In this example, we'll talk about how to set up a triple integral as an iterated integral. This is analogous to the process with double integrals. We have to think about the region we're integrating over and how to describe it correctly. Now we just have an extra dimension to worry about. So this specific example, we're given a region bounded by two surfaces. One of them is x squared plus y plus z squared equals 1, and one of them is y plus 3 equals 0. Let me show you a picture of these two surfaces. This red parabolic shape here is the x squared plus y plus z squared surface, and y plus 3 is this green plane. One thing to notice about these two equations is that they naturally give bounds for y as opposed to either of the other two variables. In other words, we can take each equation and solve for y as a function of x and z. The fact that we can do this suggests that the region is y-simple. And in fact it is. We can see this pretty visually. Here's the x-axis, here's the y-axis, and here's the z-axis. And visually, if I fix an xz value, for example on this green plane, we have a nice visual for the y-bounds. We travel from this green plane until we hit the red parabolic surface. So visually we can see that this is a y-simple region. Algebraically we can see that as well. It should be said that it is also z-simple and it is also x-simple, but I think it's a little more natural to think about this as being a y-simple region based on the two equations that we're given. So what I'll do when I set up the iterated integral is I'll pick y first, but if you want you can pick a different order. So the triple integral that we're starting with, like I mentioned, I'm going to write this as an iterated integral where I integrate with respect to y first. And then once we decide our y bound, we can think about what we want to do with the remaining two variables. But let's think about the y direction first. Visually, we can see that the lower bound is given by the green plane, and the upper bound is given by the red surface. And algebraically, that pops out with these two equations. I already kind of indicated this. These are going to be the y bounds, as long as we integrate in the y direction first. For an arbitrary xz value, the lower bound for y is always -3. And the upper bound is the red surface, which, when we write y in terms of x and z, is 1 minus x squared minus z squared. Now that we've picked the y bounds, we need to set up the remaining two directions, which are going to be x and z. In general, when you set up iterated integrals like this, you take it layer by layer. We picked our y bounds. Now we need to think about what happens in the xz region. And in general, the way we approach this is by taking the region we care about and we project it onto the xz plane. In this case, if we take this volume region that we care about and project it onto the xz plane, you can see that we're going to get a disk. The shadow of this region on the xz plane would roughly be this disk. The disk that I'm circling right now, strictly speaking, lives on the plane y equals -3. But if you take this disk and shift it over so that it lies on the xz plane, that would be the shadow of this region. Visually, I identified the projection by looking at where the two surfaces intersect. So algebraically, I can determine what that intersection looks like by determining where these equations intersect. So let me do that. This is going to amount to the fact that these are both equal to y. I can set them equal to each other and get an algebraic relation just involving x and z. So to find the projection of the region in the xz plane, we can compute the intersection of the two surfaces. Like I mentioned, algebraically, this is just going to amount to setting them equal to each other. We'll get 1 minus x squared minus z squared. That equals y, but y also equals negative 3 on the intersection. This, after some simplification, it looks like it turns into the equation x squared plus z squared equals 4. That's a circle of radius 2 in the xz plane, and that circle is the boundary circle of this disk. So here's the xz plane, and I redrew this disk, which is the projection of the region onto that plane, with boundary circle x squared plus z squared equals 4. The x and z bounds that we set up here are going to be determined by this region. Now, the region is completely symmetric in terms of x and z, so it really doesn't matter which order we pick. For example, we could decide to pick dz and then dx last, but again, you could flip the order if you want, and it'll more or less work the same. At this point, this is exactly analogous to setting up a double integral over this gold disk. If I'm doing this in the order z, then x, what do we need to think about? We need to think about fixing an x value in determining the appropriate range of z values. Fix an x value, determine the range of z values, etc. Fix an x value, determine the range of z values. When we do dz dx, we'll be integrating along slices like this initially. Well, when we do this for a fixed x, the lower bound is given by the lower half of this circle, and the upper bound is given by the upper half. That tells me that we need to solve for z as a function of x. Obviously, the whole circle is not a function of x, but there are two individual pieces that are functions of x, given by the positive and negative square root of 1 minus x squared. Here's our lower and upper bounds in the z direction. The lower bound is going to be negative square root of 1 minus x squared, and the upper bound will be the positive square root. There's our z bounds. Then we move on as usual to get the remaining x bounds. What do? We take our region and we squash it onto the x-axis. Take what we have left and project it onto the x-axis. That's going to give us an interval from here to here. And that interval is going to give us the x bounds. Because this is a circle of radius 2, we can see that the x values range from negative 2 to 2. And there you go. Lower bound's negative 2, upper bound is 2. And this is one way to write this triple integral as an iterated integral, and we're done.